one and all. I am Vishnu P, Assistant Professor, Department of Mechanical Engineering, BNM Institute of Technology, Bangalore. So I welcome you all for the second day of FDP program. So I welcome SS Mahapatra sir from NIT Rourkela, National Institute of Technology, Rourkela, for this session. Sir, shall we start, sir?
Yes, no issue.
Yes. So,
start.
Today's session, I will start with SS Mahapatra, sir. So, his topic on applications of artificial intelligence methods in optimization of manufacturing system. So, I'll introduce today's guest for this session. So, SS Mahapatra, sir, is famous for optimization techniques. So, he is professor, higher administrative grade, working in Department of Mechanical Engineering, National Institute of Technology, Rourkela. So, sir has obtained his PhD in Indian Institute of Technology, Kharagpur in 1999. So, sir has worked in different positions in the National Institute of Technology, Rourkela. So, now he is continuing as professor in higher administrative grade. So, sir has specialization in manufacturing, soft computing, neural computing, prediction tools, non-traditional optimization, and modeling and simulation. Sir has so many awards and distinguished awards for him on his papers and on his different literature work. So, sir has got 319 Scopus Index international journals, and he has guided 5 MTech students and 27 PhD students, and now he is guiding 57 MTech theses right now. So he is having administrative responsibility as first president of Student in Activity Center. So he has a nodal officer for TechCube 2, and he has got 4 patents and design registrations on his name, and he has taken 5 major R&D projects from central government. So he has also visited foreign assignments in visiting faculty of Industrial System Engineering School, Technology, Asian Institute of Technology, Bangkok, for in 2009 and also in 2012. So he is very specialized in optimization technique for the manufacturing system. So with this, I'll welcome today's speaker, Professor SS Mahapatra, sir. Over to you, sir.
Thank you, sir. Thank you very much. Good morning, all of you. Welcome to my session on optimization. One professor contacted me to deliver a talk in this FPP program. Then, as a little bit hesitant initially, because it is a sudden call from the professor Hemant Kumar, and I didn't know him. Then I thought, what type of program it will be. Then I went to the website of the institute. I was really impressed by the work that is being carried out at that institute. Then I said, okay, I can deliver a talk. So most of the participants might have attended my lectures in different FDPs. I shall be talking on the same topic on the optimization application of artificial intelligent methods in optimization of manufacturing processes, basically production processes. So before delivering the talk, I request all the participants to interact. It should be more interactive and exchange of the knowledge that is more fruitful than just listening it. It should not be one way. It should be both way, and we can interact and improve our thinking process, and it will be effective learning process. So with this, I shall start. Can you see the slide?
Yes, sir. We are able to see it.
Okay. So the topic is application of artificial intelligence methods in optimization of manufacturing systems. Now the thing is, first of all, I'm talking mainly on optimization, but the first thing is we should understand what is artificial intelligence. Since the FDP has started yesterday, and you have some idea on artificial intelligence methods and ideas of what exactly it means. We can define artificial intelligence as the ability of the computers to perform cognitive functions associated with human minds, such as perceiving, reasoning, learning, and problem solving. Uh, so, as our brain works in a similar manner, if artificially we can do some programming, then it is called, with the help of the computer, with the programming, and with the help of the computer, it will control the systems and the way the human mind thinks, then it is called artificial intelligence. And artificial intelligence, although it has started in 1950s, but the impact what we see today, continuous effort has been made from 1950s, and today we see in almost all areas of engineering we find application of intelligent systems, whether it is a mobile, whether it is a computer, whether it is online banking. Everywhere we find intelligent methods are being used. Now, the thing is, the research on artificial intelligence, when we started in 1950s, it could not um, improve for 20 years. Because the first artificial intelligence method that was used, neural network, and that time there was no sophisticated computer that can handle large data and solve the problem and give some solutions. So that time the computational interactivity, that was the major issue. So we could not improve. At the same time, parallel, computer science has been developed, computer memory has been improved, the RAM has been improved. Then, when the modern day computers become available at the desktop, then people started using the artificial intelligence techniques. More complex methods have been developed. So these are the things that we use. If you see the artificial intelligence technologies, these are mainly used for modeling of the system, diagnosis, even the medical diagnosis, use the artificial intelligence techniques. Only thing is, it is based on the data. If you see the data and find the data pattern and think as a human being thinks and extract some knowledge, then it is what a diagnosis. So diagnosis not only in the medical science but also in manufacturing, you can diagnose whether the manufacturing systems are working properly or not. So you can go for maintenance, preventive maintenance, and all these maintenance works can be done if you collect the data using the sensors. If you collect the data properly and find out, go analyze the data and find out what is to be done. Then most importantly, the prediction, forecasting of the sales forecasting, very much useful in the supply chain management. Then to make the decisions using the artificial intelligence techniques. Like, so decision science has been improved largely only use of the artificial intelligence techniques, and most importantly, the automation in any process. we need to optimize, say, for a mobile robot, the path planning. You have to optimize the path, path planning. And similarly, in flexible manufacturing systems, we use the um, we also use the path planning and optimize the system that is based on artificial intelligence techniques. These are some of the areas, typical areas where we have used the artificial intelligence techniques in um, manufacturing. That is the quality inspection and process quality control, energy management and optimization of energy efficiency, supply chain and intelligent logistics, then predictive maintenance of equipment. These are the few areas I have shown, but if you think artificial intelligence and machine learning as incorporated in all fields of engineering, and it has become a way of life now. So I'm not going to go into the details of what is artificial intelligence techniques, but mostly we use the prediction methods like neural network, fuzzy logic controller, FLC, um, which uses the if-then rules, then unfish, um, um, unfish, genetic programming, then support vector machines. All these we use for the prediction purpose. You collect the data using the sensors and whatever other things and predict the future, predict the data. Okay, predict for the futures. This is what we use using these methods, artificial neural network, polylogic controller, and fish. All these are used for prediction of the data or forecasting, prediction, what should be done. Um, then, in other hand, we use some optimization methods to optimize the process, optimize the flexible manufacturing systems, optimize the maintenance schedules, optimize the scheduling of the jobs in a job shop or pro shop. So these are the different types of optimization methods that we use based on the artificial intelligence techniques. Sometimes we call these artificial intelligent automation tools as soft computing tools, and also we call in a broader name called meta heuristics. The meta heuristic we call because we call this as a meta heuristic. The thing is that heuristic literally means it is a computerized thumb rule. Okay, it is simply computerized thumb rule. If you might have seen in the force of scheduling problem, you use Johnson's rule. There is no mathematical background. How does it work? But the thing is, it gives some near optimal solution. How to schedule the jobs so that your max span will be minimum. So that is what we use. So this is a heuristic. So when a heuristic used without any mathematical background, but based on your experience, based on your intuition, you develop some heuristic and you apply somewhere, and if it works, then it is fine, and we call it heuristic. Now, heuristic is always problem specific. For a particular problem, a heuristic is being developed. But the meta heuristics are broader, used in broader sense, but it is a generalized methodology which can be adapted to any situation or any problem. So one of the example of a meta-heuristic is genetic algorithm. Genetic algorithm, which is based on Darwin's theory, the survival of the fittest, based on the Darwin's theory. So that is what we use, and that is a meta-heuristic. So it is not limited to apply in a particular problem. Rather, it can be applied to variety of problems, but only it can be changed. The basic process remains same. For example, in genetic algorithm, we use three operators. That is the reproduction, then crossover and mutation. Reproduction, crossover, and mutation. These three operators will remain, but only thing is their functioning will be different, and it becomes problem specific, right? So it is a broad thumb rule which can be adapted to any type of problem. Now, mostly these meta-heuristic initially these were developed from these were inspired from the nature. Okay, for example, genetic algorithm is based on Darwin's theory. Similarly, particle swarm optimization is based on the behavior of the birds or behavior of the fish swarm or bird swarm, like that. So that is a particle swarm optimization. So these were inspired from the nature mostly, and we developed some meta-heuristics which can be used to solve variety of problems. Now, Now, come to the optimization. In optimization, we come across two types of optimization. One is called continuous optimization and continuous optimization, where we use we have we have some equation or objective function. Now that is to be solved, and we find out the values of the variables or decision variables involved in that. That is x1, x2, x3, these variables. We want to find out what is the best values. This is called a continuous optimization problem. In contrast, continuous optimization problem will come across in many production processes. For example, in electrical discharge machining, we want to find out what is the maximum material removal rate. So material removal rate will be a function of your discharge current, pulse on time, pulse of time, duty cycle. So many variables are there. So we find out what is the discharge current, voltage, optimum discharge current, voltage, so that your MRR will be material removal rate will be maximum. This is what a continuous optimization problem. In contrast, we come across say combinatorial optimization problem, then group technology, finding out in cellular manufacturing, finding out the grouping of the similar machines to be grouped together. Okay, so similar parts to be grouped together, and to manufacture, that is a make a part family. To manufacture part family, to assemble, you arrange the machines. So that is called the machine cell. So in group technology, we use the combinatorial optimization problem. Similarly, in a scheduling problem, in a close-up scheduling problem, it is a combination of the jobs that will give you the minimum span. So in a scheduling problem, in timetabling problem, an airline scheduling problem, train scheduling problem, bus scheduling problem, an assembly line balancing problem, we use the combinatorial optimization problems. But the meta-heuristics can solve both the continuous optimization problem as well as the combinatorial optimization problem. Only thing is their operators will be different, but the overall structure remains the same, right? So these are the way we do optimization, and optimization is a very broad area, and the work has been optimization theory is rich in many algorithms, and we can define the optimization methods in two ways. One is classical optimization techniques, and another is the non-traditional optimization techniques. I shall talk to you what is the difference and how they differ. Now, first come to the how does you define an optimization problem? And a nonlinear optimization problem can be defined either maximize or minimize. Y is a function of x. X is a vector. It's nothing but it is a x1, x2 up to xn, where there are n variables. We write x1, x2, x3 up to xn. So x is a vector of these decision variables. So y is a objective function, which is nothing but function of x, subject to some constraints. So there may be some inequality constraints. So here we have shown m inequality constraints and p equality constraints. So this is a generalized generalized optimization problem. Now all the variables x1, x2, x3 up to xn, that will be within some limits, within the lower limit and the upper limit, within the lower limit and the upper limit. So this is called variable bounds. So now this is a generalized optimization problem. Now in this case, we have only one objective function, only fx, only one objective function. When you have multiple objective functions, we call it as a multi-objective optimization problem. So we may have y will have a vector of objective functions f1x, f2x, f2 up to a few number of objective functions up to f2x. So in this case, either all objective functions may be maximized, or all may be minimized, or some may be maximized, or some may be minimized. But it is better to solve such type of problems when you bring to all the objective functions at the same level. That is, all the functions to be maximized or all the functions to be minimized. Now, to change an maximization problem into minimization problem, say maximize fx is same as minimize minus fx. So multiply by -1, then the maximization problem will be converted into minimization problem, or minimization will be converted into maximization problem. Or you take the reciprocal. So maximize fx is same as minimize 1 by fx. So that is reciprocal also we can use. It is better to solve multi-objective problems, multi-objective optimization problem. If all the functions are in similar nature, it is easy for solution. Now we will have if I remove these constraints, inequality constraints and equality constraints, then we can have a we can have a unconstrained optimization problem, right? We will have unconstrained optimization problem. If you add these constraints, then we will have a constraint optimization problem. Now, if you look at a problem, the solution complexity depends on how many constraints that you are having. It is not difficult to solve an optimization problem having many variables. Rather, it is difficult to solve a problem which are having more constraints. So linear programming is also an optimization problem in which all the objective function and constants are linear in nature. Okay, in this case, when you have solved linear programming problems, so it is not difficult how many decision variables that we are having, how many x1, x2, how many decision variables you are having. Rather, it is difficult to solve if you have more number of constraints, right? So now come to traditional optimization problems. So traditional optimization traditional optimization methods, they use the direct search methods to look at the optimum point. So some of the examples are region elimination method, interval hopping method. These are different methods where the direct search methods are there. Another method is the indirect search methods, or we call gradient based methods. So Newton Newton Newton-Raphson method, dissection method, these are the indirect or gradient-based methods. Now, in the gradient-based methods, we find a gradient. Gradient means nothing but the slope. We find the slope. If we get the slope, then we search around that direction to get the optimum point. So now, when the optimization methods, classical optimization methods are so rich, then why do you go for the non-traditional methods? Why do you go for the meta-heuristics, which are inspired by the nature? Why should we go for that? Okay, so this is very number. Look at a single objective function problem, and there is no constant, unconstant optimization problem, only having one objective function. This is what fx. If you find it, if you plot the fx, it is having only one variable, and our objective is to minimize fx so that find out the x value so that fx will be minimized. It is an unconstrained problem. There is no unconstrained problem, only one objective function, single optimization problem. Now, here, if you plot it, you find that the minimum, we are finding out the value of x in such a manner that fx will be minimum. So we have get the minimum here, we get the minimum here, we get the minimum here. Now, if you look at this point, this is called a global minimum, and these points are called local minimum. Now, traditional optimization methods, particularly the gradient-based methods, we search from a particular, some initial value and go on moving, go on searching, searching the global minimum, but we may stuck up. We may stuck up at a local optima because your slope of the gradient becomes very small, very, very small. If you do not get any gradient or the slope, then the search stops there. You cannot search. So it may be, we may trap at the local optima. We may not reach at the global minimum. So that is the problem with the traditional optimization problem. So that's why new methods have been developed. New methods have been developed. How to find out the global or search for the global minimum or maximum, whatever is the case. So that's why meta-heuristics or artificial intelligence methods or the non-traditional methods or soft computing optimization techniques, they have become popular over the years. For last 30 years, so many methods have been developed and they have been used. Now, come to how the classical optimization techniques, traditional methods that work. Now, I have given take a function. It is called a Rastrigian function. Now, it is xi square minus 10 cos 2 pi xi plus 10. Now, where b is the dimension of this value, so you can have b maybe maximum 10 you can take what the Rastrigian function says, but for this example I can take only d equal to 2. So this equation becomes, it is an unconstrained problem, there is no constraint. It becomes x1 square minus 10 cos 2 pi x1 plus 10 plus x2 square minus 10 cos 2 pi x2 plus 10. If you plot this with x1, x2, the Rastisian function looks like this. It is a multimodal function. Many modes are there. And you see the minimum will be somewhere here. Very difficult to search, but the traditional methods works. Now the variable bounds are given where x1 will be between minus 5.122 plus 5.12. Similarly, x2 will be minus 5.122 plus 5.12. Now, the value is known for this problem that a fx value, minimum value, global minimum value for fx is equal to 0. Okay, that is equal to 0. Fx is known. Now, let us solve such type of problem using a MATLAB function. So now you see, these are the in MATLAB you find an optimization toolbox. So in the optimization toolbox, we can solve many constant problems, unconstant problems, many problems we can solve. So I'm showing just an example how to solve one unconstant problem using MATLAB. So we run it. So this is the function. Here the options will be given. Options. Here the objective function f min unc. That objective function will be should be there in your directive. Okay, algorithm quasi-Newton. Then these are the standard way of standard way of finding out. Now solve it, then we can get the values. Okay. Now look at the values of x. Okay. So look at the values of x. We got the x1 equal to 0, x2 equal to 0. Then function value, we look at the function value, that f value equal to 0. This is what the optimum value is in the traditional optimization techniques. So in the traditional optimization technique, we have used f min unc. Unc means unconstant. F min means function minimization. So that is there in the MATLAB. Only your objective function you have written here at a u obj fun that you have written. So, but let's find out u obj fun here. So this is the objective function that we had given. F equal to x1 square minus 10 cos 2 pi x1 plus 10 plus x2 square minus 10 cos 2 pi x2 plus 10. So this can be solved using the MATLAB. You can use the MATLAB toolbox also. I have shown here for a better explanation. So in the traditional way, you can solve such type of problem. No, however, in the traditional problems, traditional optimization techniques, there is a problem of trapping at the local optima. So what we do, we search from multiple points instead of a single point. We search from the multiple points. So that's why this latest artificial intelligence techniques that have been developed, and we search from multiple points. So if you see the nature-inspired techniques or artificial intelligence methods of optimization, then you see there are evolutionary techniques, swarm intelligence techniques. Evolutionary techniques, that is the evolution theory based on theory of evolution, that is the genetic algorithm. Okay, then swarm intelligence techniques, that is particle swarm optimization. Then physics-based techniques, that is the gravitational search algorithm, which is based on the Newton's gravitation law. Then human-related techniques. One example is the teaching learning based algorithms. If you look at these nature-inspired techniques, which can be applied to both unconstrained, constant problems, multi-objective problems, single-objective problems, and continuous optimization problems, um, as well as combinatorial optimization problem. Only you have to change a little bit to suit to your problem. Now, all the methods that you can classify into four types. One is the evolutionary techniques, that is the genetic algorithm, which was developed by John Holland in 1960s. Differential evolution techniques developed by Stone and Price in 97. Then there are a lot of swarm intelligent techniques. If you go through the optimization literature, you'll find that many swarm intelligence techniques. So most popular in popular techniques are shown here. That is the artificial bee colony that was developed by Karabag et al. In 2005. Particle swarm optimization proposed by Kennedy and Everhart in 95. Artificial immune system. It is based on the immunity being developed in the human body. So how the antibodies are being developed based on that. So antibody here means you copy or mutate more solution of the good solutions. So that is the artificial immune system developed by Castro and Juven in 2002. Moth flame optimization, Mirjal-E developed in 2015. Firefly algorithm developed by Yang in 2008. Coco search developed by Yang and Deb in 2009. But recently, if you find people are focusing on physics-based techniques. So, because evolutionary techniques and swarm intelligent techniques, they have a lot of research has been done, and it is almost a saturated field. So people are trying to develop physics-based techniques. That is the simulated annealing, which was developed long back, but it is a very slow process. It was developed by Kirkpatrick et al. In 1983. Then harmony search algorithm developed by Dean et al. In 2009. Gravitational search algorithm proposed by Rashidi et al. In 2009. Water web optimization proposed by Zhang in 2015. So these days, we look for physics-based techniques and finding better solution compared to the evolutionary techniques or the swarm intelligence techniques. And there are other human-related techniques which is based on the teaching learning process that was developed by that is known as the TLBU or teaching learning based algorithm, TLBU, that was developed by Rao et al. In 2011. Then recently Rao has proposed a Jaya algorithm. So many algorithms have been developed. So we shall go through very few algorithms. These are some of the nature-inspired techniques have been shown, but I shall be talking mainly on practical swarm optimization, teaching learning-based algorithm, simple optimization algorithm, and harmony search algorithm, and apply to different manufacturing field. Okay, so first come to the simple optimization technique. Now, if you look at the optimization techniques, what has been developed these days, we have a lot of technique-based or algorithmic parameters, which is specific to the algorithm. Now, once you tune these parameters, then only you can get good solution. But tuning the parameters takes a long time. So that's why what the people are looking for, if the number of tuning parameters are less or very few, or it becomes parameter less, then solution, we can get the solution quickly. So most of now the focus of the days is to how to reduce the number of cleaning parameters still to get the good solution. So this is what we think about these days. Now simple optimization, which has developed um, uh, re- um, very recently, simple optimization technique, which was developed in 2012 by Hassan Sevi and Ajay. Um, so then it has been proposed. Now, in any optimization problem, when you go for the multi-point search, we look for what we reach at the optimum point. Now, when we are away from the optimum point, we give a large jump. That is known as exploration. Okay, it is known as exploration. But in the vicinity of the optimum, we there is exploitation is more important, where we look for near research the best solution for the in the near neighborhood, research for the best solution in the neighborhood, and look for the best. So this is known as um, exploitation. Large jump when you give, that is known as exploration, and when you search nearby, then it's called exploitation. So in any algorithm, we should have efficient exploration and exploitation. Then only your algorithm is good. So similarly, in simple optimization algorithm also, we have exploration capability and the exploration capability. So we use in this problem, in this algorithm, we use only two equations, nothing else, only two equations. That is the your value new new value will be the x I best plus a parameter c1 into ri, and use another equation xi new is xi best plus c2 into ri. C1 and c2 are the constants, and it is c2 is just half of c1. So basically only one constant, one algorithm constant is there. Okay, one algorithm parameter is there. So now this Ri is a randomly normally distributed random number with mean 0 with a standard deviation. Okay, sigma I is the standard deviation of I parameter for all the members in the population. Now it will be better if you can solve with an example. Now come to an example. Now suppose same Rastisian function that we have taken, the Rastisian function that I have told you is the Rastisian function, and you take here b equal to 2, that is your objective function is x1 square minus 10 cos 2 pi x1 plus 10 plus x2 square minus 10 cos 2 pi x2 plus 10. This is and we want to minimize. So we have taken this Rastisian function with d equal to 2, and all the parameters x1 and x2, all the variables x1 and x2 will be lie between minus 5.12 plus 5.1. So for the initial solution, what you have to do, you fix the population size. So here we have taken the population size of 8. So 8 number of solutions will be randomly generated initially. Okay, so we randomly generated 8 number of solutions. For x1, we generated a solution of x2. So x1, x2 solutions have been generated, and these were put in this Rastisian function, and we found out the fx values, objective function values. If you look at this solution or initial solution, what we have got, the best solution that we have got is when x1 is minus 0.14, x2 is 0.16, and fx value is 8.3127. Now for x1, we calculate the mean, for x2, we calculate the mean, then also calculate for this population, whatever the x1 values have been generated for 8 solutions, 8 population. Then we calculate the standard deviation. For x2 column also we calculate the standard deviation. Next is to generate a new solution. If the new solution is better than the old solution, that will enter into the solution, otherwise we will reject the new solution. Right? So now generating a new solution, we have to use the formula, that is xi new equal to xi best plus c1 into ri. That is the formula that we will use. So that we will use. Now here you see that this ri is a normally distributed random number. Normally distributed random number with mean 0 and some standard deviation. So what we have to do, how to generate the normally distributed random numbers. Normally distributed random numbers will be generated by using this formula. So any one formula will give you this normal random numbers. So Z1 is a normal variate. So that is twice ln R1, where R1 is to the power 1 by 2 sine 2 pi R2. R1, small R1 and R2 are random uniformly distributed random numbers between 0 to 1. Okay? Uniformly distributed random numbers between 0 to 1. Now, for generating the normal random variate Z1, either you can use the formula Z1 or you can use the Z2. Now, normal distributed random numbers Ri will be equal to mu plus sigma Zi, where mu will take the mean 0 plus a sigma, that is the standard deviation in the population, what you find, and Zi, what you generate from here. Okay, so for this example, let us generate Z1 using this formula. Z1 is 0.4781, Z2 is 0.4153. So R1, normally distributed random number that we generated for the changing in the x1 column, x1 value. So that is 0, mu equal to 0 plus sigma you see 1.8821. So 1.8821 multiplied by Z1, that is 4781, that is 0.8998, R2 again 0 plus then sigma 2 is 1.8543 multiplied by Z2 is 0.4153, so 0.7701. So two random normally distributed random numbers have been generated. Now one is for the x1 and another is for x2. Now x1 new will be, that is the xi best. What is the xi best? That is minus 0.14, minus 0.14. C1 you take 1.5, then R1 that we have taken, we have calculated here, that is 0.8998, so it becomes 1.21. Similarly for x2, mu will be, that is previously it was xi best, x2 best is the 0.16 plus C1 is 1.5, then 0.7701, we calculated R2 here. So 0.7701, so it is 1.32. Now we put the values of x1, that is 1.21, and x2 1.32 in this formula. We found out that it is 24.9774. So when you get this one, then you remove the worst solution. The worst solution that we found out is this one, fx in the initial solution, that was fx is 61.3899. So we will remove that solution and that will be replaced by the new solution, that is x1 of 1.21, x2 is 1.32, fx is 24.9774. Now, once you get the solution, then again calculate the mean, then calculate the standard deviation of the solution, then calculate Z1, Z2 values, R1, R2 values, then you put, then you find out the new solutions. Now, while finding a new solution, we will here use that C1 value what we had taken previously 1.5. Now we take 0.75. Now we find that it is x1 is 2.20 and x2 is 1.90. We put in the formula, that in the fx value we find 17.2697. Now the worst solution so far, whatever the worst solution, that will be replaced by the new solution. So now these two steps, in the first step is this. In the first step, we use after the first step using the C1 equal to 1.5, you got this solution, list of solutions. Then next is the using C2 as 0.75, you got this solution set of solution. Then these two becomes one iteration. Okay. Now this iteration will continue till you get the best solution. This iteration will continue till you get the best solution. Now we have done some research on SOPT. We found that whether we will take C1 as 1.5 or not. So what we did, we solved many problems, say 25 problems, unconstant problems we have solved, standard problems, and C1 value changed from 1 to 3, then, and the initial solution we have taken 50, or the population size we have taken 50, and then try to solve the problems. Then we found out what should be the best value of C1. You see that has been plotted in the histogram here. We found that when C1 is 1, we can solve only best solution so far achieved, that we can reach only for 16 17 solutions. But when we use 1.5, almost 25 problems have been solved. When we use C1 equal to 2, only 10 problems being solved. So we found that C1 is the best. C1 equal to 1.5 is the best as far as the SOPT is concerned. Simple algorithm. Now we solved many unconstant problems. These are the benchmark problems, 25 problems that we have solved. These are the 25 problems. Okay. Now, if you look at these functions, this D stands for dimension, C for the characteristics, C is the unimodal function, N is the multimodal function, S is the separable functions, N is the non-separable function. So dimensions are given here, and characteristics, whether it is unimodal or multimodal or separable or non-separable, these are given. The range of the variables that is given. These are the standard problems, benchmark problems that is available in the literature. So the example that I had given for the Rastrigian function, look at the Rastrigian function. Okay, it is a multimodal function, separable function. Okay, and D value is 30. Now we solve these problems. Now once we solve, this is what the result that we have got. Now this is the actual known solution so far. Okay, then what is the particular swarm optimization gives the results, and the results given by the simple optimization, the present methodology, and this is the solution given by the teaching learning based algorithm, teaching learning based optimization algorithm. So we compared with uh, to other algorithms and compared with the actual value also. Now, this is the results for while solving these problems. What is the time taken by different algorithms, PSO, SOPT, and PLP? What is the values that is taken? Now, um, when you solve the problems using and compare with the algorithms, it should be solved with the same environment. So it was all the algorithms were coded in MATLAB 7, and it was solved using laptop having 2.93 gigahertz per 2 processor and 3 GB RAM. Then the termination criteria is kept at function evaluation of uh, 5 lakhs. Okay, 5000. Okay. Now, the results correct up to 3 decimal places were taken. Now that after this um, initial assessment of this algorithm while solving 25 unconstant problems, what we have seen that other in the results, it is found that SOPT algorithm is able to reach best known solution for 21 problems, while TLB reached to best known solutions for 20 problems, and PSO reached best known solution for 15 problems. But very interesting, this Equation and Matthias functions, which are unimodal with flat surfaces, are getting solved by all the algorithms. But the difficulty lies with solutions to functions like Prestigine, Rivan, Schwaffel, and Ackley, which are having large dimension and highly multimodal, are difficult to achieve by all the methods. But the TLBO algorithm is able to get the exact solution for Rosenberg function for which no algorithm has achieved so far. Then, if you look at the computation time, it is found that PLBO performs well and reaches to 13 solutions at less time compared to SOPT. SOPT takes less time compared to TLBO in solving 12 problems. SOPT reaches solutions to 14 problems in less time against PSO, which performs better in 7 problems in terms of computational time. So these are the solution that we got. So now what we find that SOPT is a potential candidate technique that can be used in any optimization problem. So we have tested for the continuous optimization problems and also solved many other problems, but still it has not been solved using the um, for a combinatorial optimization problem. It has not been yet explored. So that is the area where you can use the SOPT um, in combinatorial optimization problem. But more or less it has been solved in many problems. Now, if you, I have told you that you have some function which is a flat function. Now, if you use some function is given by this, there are two variables, x1 and x2. Now, fx value is known as the best value, meaning as this function, fx value is known to be -1, and it is obtained when x1 equal to pi and x2 equal to pi. Now, this function we shall solve using MATLAB, using SOP. Okay. You see, that is the x1 value is 3.14, x2 value is 3.14, that is the pi, and fx equal to -1. And when you solve this equation function, it is this type of curve is known as the convergence curve. So in any optimization, whether it is working properly or not, we should show this convergence curve. Okay, so it should converge to the solution, and solution started fx value started somewhere here, then it go on decreasing, 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 decreasing like this. Then at the end, after around 250 iterations, it has come to -1. Okay, this is a iteration up to 500 is given. So after around 250 iterations, fx value is -1. Right? So this is the way you can solve. Now, teaching learning based TLB algorithm is based on a teacher is teaching a group of students. Now the students will score the marks in different subjects. Say physics is a subject, maths is another subject. So number of variables is equivalent to the number of subjects that we are having. Now each student will get a score in each subject. So value of x1. So x1 we can call maths. x1 maths. In the maths, x1 value, some value you get. Say x1 value, x1 equal to so 0.1 or 0.2, something like that. So similarly x2 relates to physics. So some score we got. Okay, in an examination. Now in the teaching learning process, what happens? The students get the knowledge from the teacher. Teacher imparts the knowledge and they get the solution. Then they improve the score in their respective subject. Similarly, the the students among themselves they can exchange their knowledge and they try to improve. So it is two way. One is the teacher is imparting the knowledge where they can improve, and also they interact each other, they can improve the knowledge. So teaching learning based algorithm, TLB algorithm, is divided in two phases. One is the teacher phase, where through the teaching of the teacher, the students try to improve their score in each subject or in each variable, and among their interactions, they improve. Okay, so this way, this way, the teacher's phase and the student's phase both make one iteration, and we go on solving like this. So this is one of the initial solution. Again, we have taken the Rastrigian function with 2 dimensions only, and the solution we have got. Then using the formula given by the algorithm, then we can improve. In the teacher's phase, we can improve. So the worst solution will be replaced by the solution. This is what after the initial solution, the modified solution has been generated. Then we come to the learner's page. In the learner's page, we compare each solution with the other solution and try to improve the solutions. Then once the learner's teacher's page and the learner page is completed, then we will get the solution. One iteration will be completed. After one iteration in this example problem, we got such type of solutions. Okay, so this is the way the TLBO works out. Then again, that equation function we try to solve using the MATLAB. Okay, we got the solution. This is what the convergence curve we got. Now you can see the values here. X1 equal to 3.14, X2 is 3.14, and this is the y value that we got, that is the -1 that we got. Okay. Only thing is, idea is that how can coordinate and solve different purposes. Similarly, the particle swarm optimization, it is based on only one equation. So before going to the particle swarm optimization, I can tell you that particle swarm optimization was based on the behavior of the plucking behavior of the birds, or the fish schooling behavior. What they do, when the birds find a food source, then all the birds, a swarm of birds, rush all of a sudden come to the food source. Now just imagine, suppose birds are sitting on a trunk of a tree. Now we can define these birds as particles. Now each particle is on the trunk of the tree. Then we can define its dimension of the position of the bird, that is x1, x, y, and z. That coordinate we can keep. So when it is sitting on a tree, so the position of a bird can be represented by three axes: x1, x2, x3. So the positions you can know. Okay. So the dimension means the number of variables you are having. So we are taking the example, a bird is sitting in a tree. So three axes you can define. It can be multi-dimensional also. So when there are 5 variables, then we will have x1, x2, x3, x4, x5. So there is a hyperspace. Having 5 dimensions. Now each bird has a position x1, x, y, z. Now we take some 10 birds. 10 birds are sitting. So these are the initial solution. Okay, we can define the value of x, y, z. Now our objective function f is a function of x, y, z. Okay. Now when the bird find a food source, the birds can change their position with a velocity and reach at the food source, right? So when they reach at the food source, that is, they have reached in the optimal solution. Now the birds change their positions, so the value of x1 and x2, x3, whatever the decision variables you are having in the fx function, that has been changed, and then they come with a velocity, right? Now by doing so, what happens? The birds exchange the information among themselves, right? So what are the birds so far achieved the best solution? That is the local best, or we call particle best, of P best. And as a whole, whatever the best solution is a swarm, or the population size, whatever the best, that we call global best. Now changing the velocity, we have suppose at the iteration t, now particle I, that is the bird I, in the jth dimension, that is the x1, x2, what is the function, or x, y, z, whatever the function that we are having. So in the jth dimension, how it can be given? That is given by w, and inertia weight w, t minus 1, v, ij, t minus 1 in the previous iteration, plus c1 is a parameter which is known as a cognitive parameter, c1. R1 is a random number between 0 to 1, uniformly distributed random number. Pij, particle best, then Gij, the position values, plus C2 is a social parameter. R2 is R2 again, the uniformly distributed random number between 0 to 1. Gij is the global best. So far, among the particles, in all the in that population, which one is the best one? Among them, what is the global best? So Gij t minus 1 and Xij t minus 1. So this is the way the velocity is changed in all directions. Okay, in all dimensions. In dimensions, how the velocity is being changed. Now, when the velocity is being changed, the position can be defined by previous position plus this velocity. So the particles change from time to time, their positions and velocities, then they reach at the best solution. P best is the personal best, and G best is the global best. Now C1 and C2 are known as the cognitive and the social parameter respectively. So W is a control parameter, which is known as the inertia rate. Initially, we give inertia very high inertia rate, and when you go towards the solution at the end of the solution or iteration passes, as the iterations move, then velocity value of W go on decreasing, and this decreases. We can equation like this: W equal to W max minus W min by iteration max multiplied by x. So in each iteration, W down changes. We will start with a very high value. Then initially the large change in W value occurs, but towards the end of the solution, as the iterations passes, the value of W decreases. Okay. Now suppose again we take the Aristotelian function. We have two variables, x1 and x2, and the don't take the yes, we take the Aristotelian function, then x1 and x2. Then here we have taken c1 equal to c2, social and cognitive parameters equal to 0. Then initially generate these position values x max and x min, that is between 0 to 1. Similarly, generate the velocities between 0 to 1, and then find out the objective functions. To take x1 and x2. These are the initial values are generated using randomly generated. Okay, velocity and the position values randomly generated. When you put this position values x1 and x2 in the objective function, you get the objective function values. So far, x1 is equal to 0.0034, x2 equal to 0.8533. We get the best fx minimum fx values 4.6866. Now, in the next, what we do, that is change the update the velocities, update the positions, then we will get a new list of solutions, then choose the personal based and the global based, then go on doing the iteration like this. So this is what a MATLAB code is given for practical swarm optimization. Okay. Okay. So x1 equal to 0, x2 equal to 0, and fx equal to 0. Okay. This is the objective conversion score. So this is the way we can solve. Similarly, so many algorithms have been developed. Now, very difficult, we have found a very constant optimization problem. Now, constant handling is really a tricky job. It is really tough. You might have seen the handling of the constraint in linear programming problem. This constraint is really tricky job. Now, you can use the best constant handling system is the priority-based ranking method. Of course, there are many methods of constant handling is there. So, uh, like repair strategies. There are many ways of constant handling. Um, so these are the most widely used the constant handling problems: the rejection of solution by violating the constants, repair of infeasible solution, apply penalty to the solution violating the constant, and apply some rules to rank the available solutions. So these are the methods, but I suggest to use the priority-based ranking methods. So these are the methods that for constant handling we are having. Now, now let us come to some of the examples where you can use these optimization techniques in optimizing the manufacturing processes. Here you see the constant handling, multi-objective functions sometimes, and also single objective functions, and with some variable um, variable um, limits. Now the question is that manufacturing processes are really complex processes. Now in manufacturing processes, these complex processes, we can very difficult to get analytical solutions. Okay, so for example, in ultrasonic machining processes, now ultrasonic machining processes, what happens? There is a horn where ultrasonic vibration will be there and a slurry will be there. Okay, now the hard materials can be machined using the ultrasonic machining processes. So in the ignition process, low frequency electrical energy is first converted to high frequency electrical signal, which is then fed to a transducer. The transducer transforms the high frequency electrical energy into mechanical vibration, which are then transmitted from energy focusing device known as the horn or tool. This causes the tool to vibrate along the longitudinal axis at very high frequency, usually greater than 20 kilohertz. So for efficient material of material removal, the tool and holder are so designed, considering their mass and shape, that resonance can be achieved within a frequency range capability of the machine. So a controlled static load is applied to the tool, and abrasive slurry, as I told you, abrasive slurry, mostly composition is silicon carbide, boron carbide, and aluminum. These are suspended in all over that is pumped on the cutting job. So the vibration of the tool causes the abrasive particles held in the slurry between the tool and the workpiece to impact the workpiece surface and causing the metal removal by microchipping. So this is what is shown here. Okay, this is the tool and a workpiece. Metal is being removed. So controlling power supply and the converter, coupler, form. Okay, so now here you will find 5 decision variables. There is the maximum displacement of a vibrating tool from its mean position, AB, that is in mm, frequency of the vibrating tool, FB, that is in hertz, mean diameter of the abrasive grain, diameter, that is in mm, concentration of abrasive particles by volume in slurry, CAV, and static heat force applied to the tool, FS. So the mathematical model, this is an analytical solution. We remember for the ultrasonic machining process, analytics is the solution given by reference 17, that reference is given. They have seen at all. They have developed this model, analytical solution for maximization of material removal rate using these 5 variables: AB, FB, DM, CAB, FS. These 5 variables that taken now subject to roughness surface constraint. The constant is 100 here, and a range of all these variables that is given here. AB will be between 0.0052 to 0.1, FB will be 10,000 to 40,000, DM will be 0.007 to 0.15, then CAB is 0.05 to 0.5, FH is 4.5 to 4.5. Now, how could you get these variable ranges? Range of this variable that has been found out what we can control with the machine. Okay, what is the machine? Whatever the machine that we can use, what is the control that we can do? So, depending on that, these variable bounds are being, being defined. Now we have to solve. Now, while solving such type of problem, some of the here you see some of the constants that has been used, that is AP, sigma FW, so many constants have been used. These constants you have to define. Cross-sectional area of the cutting tool, 80, if you take as a 20 mm square. First trace of abrasive particles made of silicon carbide, sigma FP, that is 28,000 MPa. First trace of work material, which is tungsten carbide, sigma FW, that is 6900 MPa. A constant proportionality equal to the ratio of diameter of projections on the abrasive plane to square of the mean diameter of the abrasive plane. K USM, that is 0.1 mm minus. Then allowable surface roughness, RA max, is 0.8 micron, and indentation ratio, lambda, is 0.246. So if you change these constants, then the results will be different. But you cannot change the some of the sigma FP, sigma FW, that you cannot change. But KUSM and RM max and lambda, these can be changed depending on the process and the machine, that can be changed. So now if you solve using different methods, one is the harmony source method, particle swarm optimization, teaching learning based optimization algorithm, then SOPT algorithm. We'll look at the variables, what are the variables that define, and material removal rate. Now you got the material removal rate marginally higher in SOPT, that is 4.006, and RA, that is the surface roughness, is 0.8. TLBO gives material removal rate 4.004, and RA is 0.799. But PSO and HS, they give somewhat less material removal rate compared to the other algorithms. So it is only that very small amount difference is there, but SOPT gives good solutions. Good solution. Similarly, we come to another type of machining, that is wire electrical discharge machining process, in which the wire cuts the material between the sparking between the workpiece and the wire. Okay, so this is the schematic diagram of a typical WDM setup is given. Now here we take 4 variables, that is the pulse on time and T of pulse of time, peak current, and servo field setting F. Now these 4 variables are defined as x1, x2, x3, and x4. x1 is nothing but the pulse on time, x2 is the pulse of time, x3 is the peak current, x4 is the servo field setting. Now, since analytical solution for cutting rate and the surface roughness, machining speed and the surface roughness, for wire electrical discharge machining is not so far developed. Analytical solution doesn't exist so far. It is a very complex process. So, what we do, people some experiment, use some experiment, preferably use the design of experiment approach or response surface methodology, something like that. Then develop some regression models and test the regression models whether these are statistically correct or not. They define based on the coefficient of determination, or your residual should be normally distributed. So based on that, they test the regression models and say that regression model is good enough to predict for the future, or it can be generalized, it can be used in uh, many issues, or practically it can be applied. But the regression models are basically within that environment or machining environment, it works fine. Okay, so um, so we have machining speed BM and RA. These have been um, regression equation that have been developed. So once you develop regression models like this, then these regression models can be used as the objective function, and you can find out the solution. So the range of the decision variables, which are basically constraint of the machine, or where the in that machine, what is the variation that we can make on pulse on time, that is, you can change from 4 to 8 microseconds. Similarly, TF is 10 to 30 microseconds. The discharge current is 90 ampere to 140 ampere. We can change with the machine. F can be 30 to 50, that we can change. So using these regression models, sometimes these regression models are also called empirical models. Okay, empirical models. So now that has been solved. You see, for solve with four methods: PSO, HS, harmony search, teaching learning based optimization methods, and SOPT. Our objective is to maximize cutting speed. Maximize the cutting speed. This is where the convergence curve that is shown. This convergence curve is taken from the SOPT. Okay, convergence curve. Now, RA should be less than equal to RA max, that is that is 2, less than equal to 2 surface roughness. Now see the solutions. What we find here, SOPT algorithm gives machining speed of 1.422, and RA is equal to or less than equal to 2. But if you use TLVO, it gives also gives a machining speed 1.42, but RA it is exceeding the constraint. It is above 2, whereas we have defined it should be less than equal to 2. Whereas HS and PSO, they gives less machining speed, so we need to think of that. But RA value is within the limit. So once you use the empirical models and use some optimization methods, solve it, then you have to go for some testing of it. some testing. Test these whether you are confirm the solutions, whether you are getting or not. So to do this confirmation, we have taken another example, that is the turning of titanium alloy under MQL condition, minimum quantity lubrication condition. Here also the experiments have been conducted using a response surface methodology based on box blanking method. Then variables are cutting speed, feed, and approach angle of the tool. Then we are interested to find out the responses as a cutting force, point wear of the tool, and surface roughness. Then using these data, regression models or empirical models for cutting force, point wear, and surface roughness have been developed. Then PSO is used to solve the problem, and the idea is to uh, um, um, get the solution, a weighted function of these solutions. Now, using the particle swarm optimization, what is the cutting force, plant wear, and surface roughness? These are the output properties of things, and the variables we have done. Then it has been tested again under this parametric condition. Experiment has been made, and whether we are getting the cutting force similar, what is the optimal solution that we have got, similarly with the point where whether we have got the optimal solution, or surface roughness, whether we are getting the optimal solution, that has been tested. So under MQL condition, the cutting has been made. Then come to another type of uh, um, automation where we have used additive manufacturing, that is a field deposition modeling method, and we are interested to know that improve the compressive strength of the FDM field deposition modeling build parts. So for that, experiments have been conducted. Here we have taken the FDM parameters, that is the layer thickness, sample orientation, raster angle, raster width, and the air gap, and the experiments have been conducted as per response surface methodology, and it is a face-centered central composite design, uh, and uh, the levels for each um, parameter that has been taken. Then after that, this is the data. This is the compressive strength. Once the part is built, setting these parameters at a different levels. There are 5 parameters: layer thickness, sample orientation, raster angle, raster width, and the air gap. Then compressive strength is found out. Then using this data, experimental data, an empirical model has been developed. Then that empirical model has been solved or optimized using the particle swarm optimization. Now maximum compressive strength that we got is 17.4751, and for that layer thickness is 0.254, orientation is 0.036, raster angle is 59.44, raster width is 0.422, air gap is 0.00026. Now this is what the solution that we have got, and here the part is built using the ABS plastic, and the machine used was ABS basically stands for acrylonitrile butadiene styrene, and compressive strength test is carried out as per ISO 604-1973 standard, and using a machine, Instron 1197 series machine, and um, part will abdomen parts were built using the vintage SU machine supplied by Stratasys Incorporation. So this is what the similarly we can go for abrasive jet machining. In the abrasive jet machining, uh, uh, the solutions that we have got, the uh, analytical equations that we are having. So then, um, um, then you see that SOPT is a good solution, whereas a PLBO, um, um, PLBO violates the surface roughness constant. Okay, so many optimization. I have a lot many examples that I am having, very even multi-objective functions, lot of examples that I am having. So very difficult to uh, narrate or discuss all the issues. But the main thing is what you find when you use optimization of measuring or manufacturing processes. It is really difficult to get the objective function. So try to get the objective function using the numerical methods or analytical solution methods or empirical methods. We should have a good we should have a good solution, good objective function. When you use the response surface methodology, empirical methods you develop, the only problem is that it is limited within that experimental zone. Okay, but when you use the numerical solution using ANSYS or say before all that, whatever the solutions that we can use, whatever the solution that it is sometimes it is not practicable because we make a lot of assumptions. Similarly, with the analytical solutions, we make a lot of assumptions to make the solutions tractable, and that is the difficulty to arise. But still, then people try to use develop numerical solutions of incorporating the practical limitations. And just in the objective function, instead of a objective function in an equation form, they just give the numerical solution, just embed the ANSYS model with your um, MATLAB solution methodology and get good solution. There is another important thing that we come across when you don't have a really good analytical solution or numerical solution. What you can do, it is a predictive tool. Like neural network, ANFIS, GP, genetic program, or support vector regression. You use those prediction tools. If you get a good prediction tool, if your training data set and the testing data set gives good solution or good prediction, then use that as your objective function. So in place of fx, where you give the objective function for the optimization problem, you give the neural network. If it is a good neural network, you give it a neural network. Then whatever the x1, x2, x3 values will be generated, that will be put in the neural network and it will be predicted what is the value. So it will be useful when you think nothing is predictable in the system and the system is very complex, very difficult to get the analytical or empirical solutions. Okay, in that case, very difficult to get the effects or the objective function, fitness value, very difficult to get. So in that case, you can use the prediction tools as the objective function, and we have some publications that where we have used the prediction tool as the objective function and optimized. Similarly, we have the we have some papers where we use the numerical methods as the objective function and optimize the processes. So there are so many issues, so many challenges, so many ways of optimizing the system that we come across these days. So with this, I want to stop here. Uh, I welcome any queries. If you are having, you can ask me to. No issue at all. Anything on manufacturing. Yes, please. You can ask me any question. Hello?
Yes, thank you, sir. Thank you for
Hmm.
your lot of information has been covered in a very short time, and it was
Mhm.
very informative also. I request participants, if you have any queries or if you want to ask anything to sir, it's open now.
Hello.
Yes, yes, sir. Yes, sir. Hello.
प्रोफेसर नमस्कार प्रोफेसर सुप्रभात
हाँ हाँ हाँ, नमस्कार नमस्कार।
नमस्कार सुप्रभात आपने तो बहुत अच्छी तरीके से प्रेजेंटेशन किया। मेरा नाम तो प्रोफेसर सुब्रमणी है।
हाँ, बोलिए सर।
डेवलपमेंट से ये जो मैं फैकल्टी कोऑर्डिनेटर हूँ, बेंगलोर में काम कर रहा हूँ।
सर।
ये जो अपने जो प्रेजेंटेशन में जो अलगारिदम के बात में तो बात किया था सर आपने,
सर।
आपने ईडीएम मशीन और इलेक्ट्रिक वायर चार्जिंग मशीन दोनों में बात किया था आपने। सो अच्छी तरीके से आपने जो वीडियो और ऑडियो तरफ से आपने समझाया। लेकिन मेरा थोड़ा सा डाउट है, क्योंकि मैं भी एक मैकेनिकल इंजीनियर हूँ, फैकल्टी हूँ और जो यांत्रिक कौशल या प्रशिक्षता देता रहता हूँ। लेकिन इसके बारे में थोड़ा जानना चाहता हूँ, जो अल्गोरिथम्स और जो रेंजेस है आपने जो स्टैटिस्टिक्स सब बताया, ये सब चीज तो इसके बारे में जो मिलता है ऐसे क्या सर? ये जो मशीन लर्निंग में इसमें इंटरफेस करना चाहिए या अपना जो डीप लर्निंग में इंटरफेस करना चाहिए, किस तरीके से करेंगे तो अब ठीक रहेगा सर?
सर
ये जो अल्गोरिथम्स आपने बताया सर, तो ईडीएम का, ये इलेक्ट्रिक वायर डिस्टेंस मशीनिंग का जो स्टैटिस्टिक्स दिया है सर, ये सब चीज तो क्या हम मशीन लर्निंग से करेंगे तो आसान हो जाएगा या डीप मशीन लर्निंग से करेंगे तो आसान हो जाएगा? किस तरीके से आप
सर anything you can do, sir. People have used deep learning as well as machine learning. Only the for example, I have told you that if it is a complex manufacturing process and we do not have any idea on the only we know the process parameters, but the equation we do not know. So in that case, you can in the fx function use the neural network and advanced version of the neural network. So that is a embedding of the machine learning process. We have some publications that I can share with you. How we have embedded with the optimization.
Okay, Professor. लेकिन a question. I think what I should confirm is that whether these things will have a definite effect on the type of machining or the rate of machining or the particularly one activity of that particular concept. Will it affect positively? Will it affect, sir? These particular things, statistics or algorithms, if we do through this particular network or artificial intelligence, will these things will affect actually the rate of production will increase, definitely increase. Hello. Hello. Hello, Professor.
Hello.
Hello. Hello, Professor. Hello. Can I request organizers to please help me this in regard?
Yes, sir. Yes, sir. I think sir has having some connectivity issue. I think so. He's trying to connect.
Okay.
Yes, sir.
Yes, sir. Professor, Kshama
Sir,
Chadha.
sir. Sure, sir.
Sir.
Hmm.
Sir,
Ah.
what I would like to know finally is, will these algorithms and artificial intelligence or the so-called big data will
Sir.
definitely help in increasing the rate of productivity? That is my issue.
Right, sir.
Okay.
Sir, actually, I have I have considered the optimization part, but the
Okay.
other things of the artificial intelligence application in manufacturing,
Okay.
where you can get the sensor data and use some
So,
predictive
I
tools and
think
optimize that. A complete integration I have not shown you, sir. Complete
okay.
integration I have not shown you.
No, do you optimize? So optimization by using the artificial data or synthetic data will definitely improve the rate of production.
Definitely, sir.
And
Only,
reducing,
only,
reducing the
only when there is a complex process. For example, blast furnace. The process is really complex. So in those cases, you can see how to improve the productivity of those furnaces. Where it is very difficult to get some solutions using analytical or numerical methods, sir.
Okay. Okay, Professor. Dhanyawad upfront.
Okay.
Thanks for the organizers.
Thank you.
Thank you very much.
Okay,
Thank
sir.
you. Thank you.
So any other question? Okay. Uh, Thank you all. Thank you all the participants. On behalf of management, VNM Institute of Technology and Department of Mechanical Engineering, I thank SS Mahapatra sir for your informative session on predictive progress happening in the manufacturing techniques. So it was very informative, sir. So I thank you for your deep presentation. Thank you, sir.
Thank you very much.